Welcome back, physics. In this set of notes, we're going to be learning about work, energy, and power. All three of these concepts are linked, and they're pretty similar. So we've already talked about work in class, and we have discussed that it's not necessarily the amount of effort alone, but it's also kind of about the time included. In this case, it's going to be how far we go. So let's see what this means. When we talk about work, we'll represent that as the symbol capital W, and it's going to be the force applied to an object, or the net force, multiplied by the distance that that object travels in. Now, this equation is different from some other ones because the force and the distance have to be related in a particular way, and they need to be parallel with one another, right? We can talk about perpendicular being kind of an upside down capital T. So we need the force and the displacement to be parallel. So just to help us understand that, let's say I'm pushing on a box across the floor. If I push on the box to the right and the box goes to the right, some displacement, then work has occurred. Work happens. It can also happen in the other way too. Let's say that the box is already in motion. And so that means that the force is going to be slowing it down. So let's say the force is in the opposite direction. Well, work still occurs. We would call this anti-parallel or in the opposite direction. But this still works because the force and the displacement are still on that x-axis, right? If I had my axis here, here's the y-axis. Here's the x-axis, right? Notice that the force and the displacement are still on the x-axis. They are not perpendicular. They're not in the y and x axes. So let's consider then, are there situations in which work does not occur, but one or the other components are present? So let's consider this person pushing on the wall. So because our person is pushing, right, there's going to be a force on the wall going to the right. But the displacement is equal to 0. So even though there is a force, the work completed is 0, right? You might think you are working pretty hard. You might be building up a sweat maybe, pushing on this wall, but it doesn't move. So if the wall doesn't move, then there is no work. Notice and remember that it's all about the outcome. In this case, the outcome, the physical change to the system is 0. So the work done on the wall is equal to 0. It hasn't moved anywhere. It hasn't gone up. It hasn't gone down. It hasn't gone to the right. Nothing has occurred. You've simply been exerting a lot of force on the wall, but the wall has done nothing. Next, let's consider a person holding a tray of food, like a waiter. Okay. Here's our burger. It's a square. Okay. So if we want to consider how much work is completed, well, first off, we know that if we want to stop the platter from falling, we are going to be pushing up on the tray, but our waiter is going to be displaced across the room. Well, now both parts of work are present, right? Work is force times displacement. But remember, they need to be parallel with one another. Notice that force and displacement are perpendicular, right? These are perpendicular. It makes a right angle. So no part of the force is in the same direction as the displacement. So the force here does not cause any work. The work done is 0. Now, some displacement occurs. That means work is being completed, but the work is being done by the force of friction times the displacement, right? The thing that's keeping the tray from sliding off your hand is friction. And so it's actually the friction that's going to be doing that. So it's the force of friction. So this is where the work is done. But if the force is perpendicular, well, then the work is going to be 0 if it's perpendicular to the displacement. So just like with a lot of equations that we've used in the past, there are two components to it, right? When we deal with force, it's mass and acceleration. When it's momentum, or sorry, it should be a P. When it's momentum, it's mass times velocity. When it's impulse, it's force times time. Notice all of these equations work exactly the same. There are two pieces that make up another one, two pieces that make up another one. So that's the same thing that's going to be happening here. When we're looking at work, it is the force times the displacement. So I can increase my force and increase the amount of work done, or I can increase the displacement and increase the work completed. So let's consider a couple of examples. So what about a weightlifter? Let's increase the size of our letters to represent how large the values are. Well, if I have a weightlifter and they're going to be lifting heavy weights off of the ground and above their heads, right? I would say that they are exerting a lot of force, right? Big forces. But there's not a lot of displacement, right? Right? They're only lifting it from their feet to their head. It's not going very far. So this is for a weightlifter, right? Weightlifters exert a lot of force, but very little displacement, only from their feet to above their head. Now, by contrast, the amount of work completed by someone climbing Mount Humphreys, well, each footstep is going to require a lot of force, but they're going 5 miles to the summit. So the displacement is going to be really large, right? This is hiking. A lot of work would have been completed, or hiking up Humphreys. Cool. Take a moment for yourself to fill in the third option, the book falling off the table. Is it a large force? Is it a large displacement? Or is it small for both? It's up to you. What do you think it is? All right. Now let's consider a bow shooting an arrow. Okay, so here we have our curved bow. And the arrow is being pulled back. By the string, right? Now we want to know about the work completed. How large is the force going to be? How large is the displacement? If we think about it, the bow shooting the arrow, well, if anyone's shot a bow before, you know that the force is going to be quite large, right? But the displacement only works as long as this force is in contact, right? Once it's gone, well, the work's going to be done, because work is just the force times the displacement. And it's only going to be a displacement from about here to about here, because after this point, right, well, now the arrow is no longer going to be in contact with the string. So the displacement is actually quite small. So this is very similar to the weightlifter. The force is large because you're pulling it back, and then the string is going to apply that force over a short displacement. It's going to go really far, but the force of the bow on the arrow isn't going to be present after it leaves the bow, right? We've talked about this before, that the force is only present when the two objects are in contact. So once it leaves, there's no more work completed, no more work on the arrow.